So the plan now is to go from Seth to OV, this problem, and then to problems in P. So OV, what is this problem? It's OV means orthogonal vectors. It's kind of maybe a bit of a scary name. Like, what does algebra have to do with anything? Like, we're talking, it's going to be like a very combinatorial problem and so on. So I'm going to define it like in the standard way, and then I'm going to give you a different definition that I like maybe a little bit better, which as a graph problem. It will be like extremely combinatorial. But anyway, like here's the definition. You have two sets of vectors, but they're just binary, like 0, 1. So it's like really like bit strings. They have some dimension d, and they have n. So there's n vectors in each list. So just two lists, A, B, each of size n. And there's some dimension d. And the question is there a pair, one here, one there? Can you find a pair that is orthogonal? So the inner product is 0. But what does that mean, really? I mean, these are just 0, 1 vectors. So you take the inner product. It's just like you look at every coordinate, and you don't want to see 1, 1. Like, you want to see a 0. Like, for the inner product to be 0, in every coordinate, there has to be a 0 in one of the two vectors. So it's really this, like, for every j, like from 1 to d, one of the vectors has to be 0 in that coordinate. So here's an example. Like this is, these are two vectors. These are orthogonal, right? Whenever there's a 1, there's a 0. So these are orthogonal. And then this, for example, these are not orthogonal because in this coordinate they are both 1. So if you take the inner product, you get something non-zero. So it's like, it's kind of like disjointness or something. So let me give the. So you can start thinking about how you solve this problem. So I'm going to ask you how fast can you solve this problem, yeah, we will really care about this when d is small, like the dimension is kind of polylog, but you can think of it in general, like how you would solve this problem. So here's the equivalent definition as a graph problem. So like I can just take the vectors and put them in a graph. So if I take the vectors, right, A, and I put a node for each vector here, and a node for each vector B here, and then I look at the coordinates. So I have this. It's going to be like a layered graph. And I have a node for every coordinate. So there's d nodes here. And then I take a vector and I check, does it, in the first coordinate, is it 0 or is it 1? And if it's 1, I put an edge. If it's 0, maybe I don't put an edge. If it's 1, I put an edge. And then I do the same thing here. So I'm just kind of like encoding the vectors as neighborhoods in this graph.
Sorry, what do you put in the middle of these?
These are just d nodes. D nodes, like one for every dimension. In the vectors, right, there were these d dimensions. So the vectors are like 1, 0, 1, 0. So let's say this vector, I could represent it here by saying, okay, the first coordinate is 1, so I put an edge. Second coordinate is 0, I don't put an edge. The third is 1, so I put an edge, and so on. So this node now represents this vector. Okay? So then what am I asking here? It's, what does it mean for a pair to be orthogonal? It really means that this pair, I'm looking for a pair of nodes A and B such that whenever there's an edge, here there is no edge. So what it means is that there's no path. There's no two path. It's just like looking for a pair that is far. The distance is not 2. So that's the graph definition. It's the same problem. It's just Okay, so I have this graph. It's tripart. It's like 3 layers. There's 3 layers: A, D, and B. This has size n. This has size n. This has size d. All the edges go from according to the layers. There are no edges like this, or no edges inside. It's a very special type of graph. And I ask, is there a pair 1 in A, 1 in B, where the distance is more than 2? This is exactly the same problem. And in the reductions to graph problems, this is going to be like what you want to work with. Depends on when you want to reduce OV, if you're reducing to like problems on strings and geometric points or whatever, maybe this is like a more appropriate definition to think about. But if you want to talk about graphs and stuff, this is more useful. Okay, so how do we solve OV? So the trivial algorithm is n squared d, right? Just try for every pair, you check if they're orthogonal. Here's another kind of easy algorithm. 2 to the d times n. So if the dimension is very small, like let's say less than log n, then this is not a bad algorithm. Anyone see how to do this?
You can build a lookup table for all the vectors which exist.
Yeah.
And their subsets.
Yeah. So if d is for any d, right, the number of there's only 2 to the d possible vectors, really, binary vectors. So if you just build a hash table with all the vectors that exist in the set, and then now for every vector here, you think of all the vectors that would be orthogonal to it, and you look them up in this lookup table. So there's, 2 to the d vectors total. So for every vector, you just have to check 2 to the d things. So that's why you get this running time. And the point about it is that, it's subquadratic when d is like, let's say, much less than log n. And then there's a third algorithm, which it's with this polynomial method that Nick mentioned that is used to solve SAT. And it's like a fine-grained technique. It was actually invented by Ryan Williams to give this algorithm that we mentioned yesterday. For APSP, I said there's this kind of running time for APSP. I don't know if you remember this. So that same technique, you can use it to solve OV and get this running time. Something like this. So it's like log n over d, 2 minus log n over d, the exponent. And what's cool here is that as long as d is c times log n, some constant times log n, this is subquadratic. So it's not just for d less than log n, it's for any like 100 log n, it would also be subquadratic. Just like maybe a few words about this algorithm. So one thing you could have noticed is that this problem is kind of like matrix multiplication. I mean, if you take the vectors and you put them like this, then you take the product as a matrix product, then you're checking, for every row and column, like what is the inner product. So what OV is asking you is really, the product of these matrices, is there a 0? Or is it all non-zero? So I could mention here that, so there's yet another algorithm that is like, matrix multiplication of n by d by n matrices. So you can solve this problem with matrix multiplication. It will not be subquadratic. I mean, the output size is just n squared if you do this. But if d is large, let's say d is n or root n, this is the state of the art. Like, let's say if d is n, this is some subcubic algorithm, some n to the omega. So that's good. But we will really be focusing on like d being small, like polylog, and then we want to ask, is it quadratic or subquadratic? So that is not going to help us. But this algorithm with the polynomial method, it is by reducing to matrix multiplication, except that you reduce to smaller matrices. So it's like some kind of clever thing where you kind of make matrices where the size is less than n, like n over some factors, by like somehow putting vectors next to each other, like compressing vectors into the rows, and then it becomes messy. You have to do polynomials and stuff. I'm not going to talk about it, but just so you know, it is at the end of the day with matrix multiplication. Okay. And now to the main theorem. Seth implies that this is tight. Like there's no subquadratic algorithm if this is a little bit bigger. So if the dimension is a bit larger than C log n, then then that's it. So it's like very tight lower bound here. So let me. Okay, so forget about this d, this log n and stuff. Let's take a step back. Like, think of d as just being small, like polylog n, right? So it's easy to get quadratic time and stuff. And even then, you can ask, is it subquadratic? It could be linear. Like the input size is n times d, so it could be like a linear time problem. And this theorem says that it's not. You need quadratic time. It's even stronger. It says that even when d is log n, then even then, it's kind of, it's very tight in the dimension. But it's like amazing and super useful, even if if this is just some polylog or whatever. And the bizarre thing here is that, yeah, you're starting with this exponential problem, like an assumption about SAT being 2 to the n, and you get a quadratic lower bound. So that's what we will show now. How does this work? So just to state it a bit more formally, it means that for every epsilon, there's some c, that OV with c log n. Okay, so let's prove it. So how many of you have seen this proof before? It's less than I expected, by the way. It's people. I mean, I think people have been showing it in like undergraduate courses these days, in algorithms and stuff. So but yeah, I'm happy that you'll see it now for the first time. So here's the proof. So we're given a CNF formula, right? KCNF. By the way, anyone who haven't seen it wants to guess how it works? Like, how do you go from an exponential problem to a quadratic problem? Sorry? Partition small problems like log n. No, this is the other direction. So it's exponential. Right, so I'm giving you a subquadratic algorithm, and you have to, you want to use it to get an exponential algorithm. So you have your formula has size n, and you're trying to beat, you just have to beat exponential time in n. So you can produce something exponential, like you can produce something that's like 2 to the root n, or 2 to the n over 10, or something. As long as subquadratic in that is still better than 2 to the n.
Is it like you break up your variables into 2 parts and consider all partial assignments to them?
Exactly, yeah. So, okay, so yeah, the first thing is you break your variables to 2, yes? So you had your n variables. You break them into 2. And now you try all assignments to each half. So each half has n over 2 variables. So there's only 2 to the n over 2 possible assignments to that part. Yeah. So it's 2 to the n over 2, like this. So for each half, there's 2 to the n over 2 assignments. And so it's like you generate all of them. You generate all of them here. And each one will become a vector. And then the orthogonality check of these vectors will check if the assignments that you have, if some assignment here, some assignment here, if they satisfy the formula. And this 2 to the n over 2 is exactly right. If you take that squared, you get 2 to the n. So if you get that to the power of subquadratic, like 2 minus epsilon, then you get something better than 2 to the n. So that's what we're doing. So we split the variables into 2. And now we do this. So for every assignment, alpha to u1, create vector. Okay, so how are we defining these vectors? So we look at the formula, at the clauses of the formula. So okay, so first of all, we have these assignments to half of the variable. So alpha, take some alpha. It's some assignment to this half of variable. So it says, this is the x1 is true, x2 is false, and so on. It sets some true or false value to half of the variables. And now to define the vector for this alpha, we look at the formula and we check which clauses are satisfied and which are not. So at the jth coordinate, we looked at the jth clause, and we check if this assignment satisfies the clause. If it satisfies, we put a 0, otherwise we put a 1. And what does it mean for an assignment to satisfy a clause? Right, so let's say some clause is like, x1 or x7 or not, or x30 or something. So if you look at this assignment, right, this one says x1 is true. So it satisfies this clause. It's the x1 is here, this says it's true. So because of this alpha, this clause is satisfied for sure. But then if it says x1 is false, and let's say this assignment doesn't say anything about x7 and x30, then it didn't satisfy it. It didn't falsify it. Like, it could be that some variables here will satisfy that clause. We don't know. But just like this assignment by itself, it doesn't satisfy it. So then we say it doesn't satisfy the clause. So if you look at like some alpha and some beta, and you look at the clause, you would hope that one of them satisfies it, or both. But you don't want it to be the case that neither alpha satisfies it nor beta satisfies it. In that case, the clause is really not satisfied. So that's the idea. Okay, so we define these vectors, and then so we do the same for the beta. So we define the alpha vectors, now we define the beta vectors. Okay. So I define the beta vectors exactly the same way. I look at this assignment, I go over the clauses. For each one, I check if it satisfies. If it satisfies, I put 0. If it doesn't, I put a 1. That's it. That's the reduction. Now let's analyze it. So here's the claim, the main claim. If you look at two vectors, then they are orthogonal if and only if you look at the two corresponding assignments and you take them together, they satisfy the formula. Does anyone see why that's true?
Never get ones together. So either this or that will satisfy.
Exactly. For any coordinate, which means for every clause, for every coordinate, there will be a 0. There will not be 1, 1 if they're orthogonal. So one of them satisfies. Like one of them is 0, which means that it satisfies the clause. That's the proof. So if they're orthogonal, then for every j, one of them is the first is 0 or the second is 0, which means that every j, either the alpha satisfies the clause or beta satisfies the clause. Which means that alpha and beta, they satisfy everything. Right? If they're orthogonal, then for every j, for every clause, one of them has to be 0, which means that one of them has to satisfy, which means that together they satisfy the formula, and everything I said works in the other direction. If the pair satisfies the formula, then they satisfy every clause. Then for every clause, one of them at least satisfies it. And then for every coordinate, one of the two vectors is 0, which means that they're orthogonal. So that's the reduction. And why does it prove the theorem? So what's the correctness we did? And what about the efficiency? So what is the number of vectors? Yeah, so it's easy. It's just 2 to the n over 2. Right, for every assignment to have the variables, we have a vector. And what is the dimension? It's the number of clauses, which is like linear. So we assume that it's linear because of sparsification, linear in n, which means it's of log n. Right, because n is exponential, so then linear becomes logarithmic. So the dimension is logarithmic in the number of vectors. And we got this lower bound because if we solve the problem in n to the 2 minus epsilon, then you'd get 2 to the n over 2 to the 2 minus epsilon, which would be 2 to the n to the 1 minus epsilon over 2. So for any epsilon, if you solve OV in this time, you solve SAT in this time, and this refutes SAT.
So for the dimension, we don't really need sparsification factors, even if it's like...
Yeah, that's a good point. So if this was n to the k, then what you'd get here is log to the k, I think. It's not, the k is not here, it's here. Because log n is like n. So because, yeah, log of that is this n, so you raise that to the power of k. So it's log to the k, which is fine, like it's polylog. For the consequences, most of the consequences, it will not matter. There's one interesting consequence that Nick will talk about tomorrow where it will matter, actually. For most of the cases in P, like the lower bound we're saying is like n to the 2 minus epsilon, so if you have some polylogs, it's not a big deal. So just before we go on the break, let me show you one application for a graph problem. Okay, so the graph problem I want you to think about is the diameter. You have a graph and you want to compute the largest distance. So how you solve this problem is like the trivial thing is you compute all the distances, you solve APSP, and you just return the largest distance. But diameter is just one number, and so maybe you can compute like the max distance without computing all distances. So that's like the question. Can you solve diameter faster than APSP? And specifically, think about sparse graphs. So the most basic thing, unweighted, undirected, and sparse. So the number of edges is linear, or n log n, or almost linear. So let's say diameter where m is O tilde of n. So it's like computing max. And so running all pair shortest paths in such a sparse graph is, so you run like, let's say, Dijkstra n times. So it's nm, which would be quadratic time. So this is the trivial thing is quadratic for this problem. And can you do better? Can you do faster than APSP? Like maybe you don't have to compute APSP. So the answer is no, you need quadratic time. Okay, so how do you show this hardness from OV? It's right there, yeah. That's what you're saying? Yeah, so this problem is like almost diameter, right? It's asking, is there a far pair? So diameter, like what we will show is that like showing, not even computing it exactly, but saying, is the diameter 2 or is it 3? Just distinguishing these two cases is going to be hard. And it's almost this. It's not quite. So do you see why? So I think the suggestion is to say, like, here, take this problem, like okay, OV is hard, OV is this. In this graph, if the diameter is 2, we know there's no orthogonal pair. If the diameter is larger, like 3 or more, then we know there's an orthogonal pair. Distinguishing 2 versus 3 needs quadratic time. That's it. But there's a bit of an issue. Yeah, so, right, like we don't know that the diameter is 2. Even if there's no orthogonal pair, there could be some pair, like some vertices there, that have distance 3. That would fix the issue, but then the number of edges becomes quadratic. Suggestion was like make everything into a clique. So then, like if you want to go from one thing to the other, you could just take like an edge in the clique and then go. Because currently the problem is. So currently, like the problem is, you look at let's say this node and this node. Maybe there's no two paths. Maybe they have to like zigzag or something, and distance would be 3 or.
If you said make them to a star, you get one center node, make them to a star, and then you have to connect the centers to.
Yeah. So yep, exactly. So you add some star, connect it to everybody here, and you make another star, you connect it to everybody here. You don't even have to connect the stars because they can go like this. So if we do this, then all the distances that we didn't care about, like these distances and these distances, and everything we didn't care about is 2 for sure because of the orange edges. And the distance we care about are from A to B. And the orange edges, they don't help you get from A to B in less distance 2. If you use an orange edge, the distance will be 3 to go from A to B. So if you do this, then the claim is that the diameter is 2 if and only if there's no orthogonal pair. So that's the reduction. Okay, so I have 5 minutes, so I'll tell you some story. Yeah? Great, that's exactly the story. So the story is like, so in terms of approximation, so typically when you show a hardness result, it doesn't say that the approximation problem is hard. Like, what's a good example? I don't know, like dominating set. We said, like, is there a dominating set of size n or not? If there isn't, well, maybe there is one of size n plus 1. Right? And that's a very small gap, n versus n plus 1. Like, You would like to like a multiplicative gap. Say either there's one of size n or there's one size 2n or 100n. This is something that's very interesting because it shows that not only is the problem hard to solve exactly, but also hard to solve approximately. Typically, you have to work hard for these things. But in some cases, few cases, you don't have to work hard. This is one example. So what we just showed is that 2 versus 3, distinguishing 2 versus 3 is hard. So it means that if you want 1.5 minus epsilon approximation, requires quadratic time. Uh, 1.5 minus delta. And this was like for free, kind of. It's like, you prove that 3 coloring is hard, NP hard, so distinguishing 3 versus 4 is kind of hard, so you got some hardness of approximation for coloring. It's like a lucky thing. Tomorrow, by the way, Nick will show you much more complicated hardness of approximation results for problems. But there's a nice story here because what about algorithms? So it turns out you can get 2 approximation very easily. So you can get a 2 approx in O of n time. Does anyone see how to do that?
For one, you find this in J.
Exactly. So you take this is your graph. You pick an arbitrary vertex. You compute all the distances. You use Dijkstra from that node. So then you find the furthest node from your source, it's your arbitrary source, and you return this as your diameter, your approximation. And this is a 2 approximation. Why? Because you returned this x, and suppose that the true diameter was this pair, then, this distance is less than x because you didn't return it. And this distance is also less than x. So this means that the true thing is less than 2x. So that's a 2 approximation, just the BFS. Okay. So it's like, okay, there's some kind of trade-off here. And in the same paper where they showed this hardness result, this is by Roditi and Virginia. They showed that you can get a 1.5 approx in subquadratic time. Okay. So like 1.5, you can break the quadratic bound. And it's a more complicated algorithm than this. It uses some sampling. You sample like root n nodes. You compute the Dijkstra from those nodes, and you get the estimates. You do some kind of analysis. And it's subquadratic time. But then they showed, this factor, it's tight. Like if I'm doing a better approximation, then I need quadratic time. So that's kind of cool. Like Seth, about Seth, it tells you like the right approximation kind of trade-off for diameter. And if I have 2 more minutes, I'll tell you that the story has developed since then. So there's a paper showing that this is like much more recent. Like people are trying to figure out like the exact trade-off. Like if I give you like 1.1 time, what's the approximation you can get? So they showed that you cannot get a better than 2 approximation in linear time. So if you insist on near linear time, the best thing is 2. So there's no 2 minus delta approx in near linear time. And by now, there's like a lower bound trade-off and an upper bound trade-off that look kind of the same. They don't match. They go at different speeds, but they match in certain places. And I think that's pretty cool. Like everything is under Seth, these lower bounds. Okay, so that's the end. After the break, there will be exercise. I mean, you already got the exercises. I think for like, I'm not going to show more examples here because like I think for these things, it's really like you doing these reductions, you're going to learn much more than just me showing them. So I hope you take them seriously. One thing I will say is that like with OV, when you do reductions, there's like two things you have to think about. There's the vector gadget, and then there's the OR gadget. So OV, I deleted the definition, but it's like there's this orthogonality question. Like each vector, pair of vectors, you have to check if they're orthogonal. So it's like to encode it in a different problem, you have to encode the vector in a certain way. Like you need a gadget for the vector. Here, the gadget was simple. You just like put edges. Other problems, maybe it's more complicated. You have to encode it in different ways. And then you also need an OR gadget, which is something that somehow says that you can pick any pair. So you create your gadgets, but then you combine them in a way that makes the problem choose the best pair. Like if there is an orthogonal pair, like the problem will choose it. So just conceptually, there's two steps: the vector gadget and the OR gadget. In the afternoon, I will show you some more reductions, and tomorrow we'll see more complicated reductions. So, okay. See you.